Welcome to the SD-WAN over segment routing demonstration. Today, we will showcase one of the latest innovations in Cisco's segment routing solution, per-flow automated steering. My name is Jose Liste, and I'll be your host. SD-WAN is a new approach to network connectivity that aims to lower operational costs by interconnecting sites over low-cost internet links secured by IPsec overlays. With segment routing, a network operator can monetize its rich infrastructure and offer customized per application enterprise SLA services for SD-WAN customers. And achieving this in a scalable way and without adding any per-flow state into the network. Leveraging the markings imposed by the customers or the service provider's managed edge equipment, the network operator can use per-flow automated steering in order to send application flows over the network according to their intended transport SLA. This demonstration showcases key building blocks of Cisco's intent-based segment routing traffic engineering toolkit, starting with per-flow automated steering, which provides intent-based traffic forwarding with granularity at the flow level, segment routing IGP flexible algorithms for intent-based network slicing, and MPLS performance measurement, which provides the foundation for delay-aware path computation. As one of the newest members of the SRTE family, we will focus on explaining a bit more the first one of these innovations. Well, based on the same principles of already released per-destination automated steering, per-flow automated steering takes the solution to the next level by allowing operators to assign transport SLA intent to service routes that shall receive per-flow treatment. Let's quickly review the concepts behind this innovation. The solution introduces the so-called per-flow SR policy, or PFP. A PFP could provide up to 8 different ways to reach an egress network node in the network. Each way can be realized by an SR policy that enforces a path across the network based on its seed list, or by simply following the shortest path. Lastly, the locally assigned packet's forward class value determines what way will be used. Consider as an example a PFP at node 1 identified by color blue and endpoint node 4. This PFP has 2 different ways to reach node 4. The first one, following the shortest path to 4, represented by the black line. This path will be used for packets with forward class value 0, destined for service routes steered over this PFP. Another way, representing the path that minimizes delay to node 4, depicted by the green line. This path will be used for packets with forward class 1, destined for service routes steered over this PFP. The concept will become more clear in the next slide. Let's have a look at the CLI. The slide shows a manually configured PFP called MyPerflow. This PFP is associated with color 100 and endpoint 1.1.1.4, where the color 100 identifies the per-flow intent. Notice that instead of seed lists, a PFP defines how forward classes are mapped to the desired forwarding behaviors, for example, IGP shortest path or low delay path. In this example, color 10 represents the low delay path. The slide shows a manually configured policy with color 10 and endpoint node 4 that has a path computed by VHDN that minimizes delay to node 4. Now, based on the very same automated steering concepts, a color service route is automatically steered onto an SR policy of the same color and with an endpoint equal to the next hop of the service route. In this example, consider the prefix 3/8 with color blue advertised by node 4. This prefix is associated with the policy blue, node 4. Now in action. First, consider an application that requires best effort path. The ingress PE classifies its traffic and sets the forward class to value 0. This classification is done with a service policy. As a result, traffic of such applications towards 3/8 will be steered onto the IGP shortest path to node 4. Then consider another application that requires low delay path. The ingress PE classifies its traffic and now sets the forward class to value 1. As a result, the traffic of such application, again towards 3/8, will be steered now onto the mean delay path to node 4. Well, let's now move on to the demonstration. The demonstration topology includes a service provider's segment routing enabled network composed of ASR 9000 and NCS 5500 family routers. The interconnecting links include both MACsec encrypted as well as unencrypted links. On top, Cisco NSO acts as a service orchestrator. Lastly, and in order to provide transport SLAs beyond best effort, the devices participate in multiple segment routing IGP flexible algorithm instances. One of such flex algo instances is used to build a low delay slice based on the per link delays measured using MPLS performance measurement, while another one is used to build a secure slice that minimizes the cost of transport while including only encrypted interfaces. This service provider network provides internet connectivity to a pair of sites of an enterprise customer with Cisco's SD-WAN solution. The SD-WAN edge routers are implemented with CSR 1000B. The Cisco SD-WAN controllers are also represented on the top. Without any special treatment by the service provider, all traffic originating at Site 1 and encapsulated into an IPsec tunnel towards Site 2 will be delivered over the shortest path to the egress PE, advertising the BGP route to reach Site 2. Such a path, as you can see, could traverse links with high delay or that are unencrypted. On the other hand, a service provider with optimized connectivity for SD-WAN customers could add an intent, basically a color, to indicate per flow treatment to the prefixes of such customers. In the first step of the solution, the SD-WAN edge router classifies traffic according to customer requirements and remarks the outer DSCP to indicate the desired transport SLA. Next, the service provider ingress PE with per flow automated steering classifies encapsulated traffic according to its markings and then steers it into corresponding SR policies. As a result, encapsulated traffic associated with best effort applications follow the IGP shortest path to the egress PE. Encapsulated traffic associated now with privacy-sensitive applications would follow the path to the egress PE over the secure network slice implemented with FlexAlgo. And lastly, encap traffic associated with delay-sensitive applications follow the path over the low-latency network slice, also implemented with another FlexAlgo instance. We end up with one service and multiple transport SLAs. Let's now move on to the demonstration. In this screen, we have a SRTE user interface that basically displays the same topology I was showing you earlier in the slides. There are a number of routers that have different color icons. If you look at the blue routers like London, are routers who do not have any MACsec encrypted facilities, where the rest of the routers in the topology do have either MACsec only links or a combination of unencrypted and MACsec links. This topology is being depicted in the UI thanks to the topology that has been collected and shared over REST APIs by Cisco's srPCE on the top of the drawing. The SD-WAN customer of this demonstration will be connected into the PE routers called Dublin on the left-hand side and Frankfurt on the right-hand side. Let's actually click on Frankfurt as an example. Well, Frankfurt will be a node that actually has one loopback, 31.31.31.31, and it has multiple labels associated with that loopback. As you can see on the last column, the labels represent the segment routing algorithm that they represent. Algorithm 0 as the regular algorithm for SR, and then you have two FlexAlgo instances, 128 and 130. We will describe what those FlexAlgo instances do. Pay attention to the different label values, 17,031 and 18,031. If I were to go into Dublin, I will find similar arrangement. One loopback, 28, 28, 28, 28, and three labels across three different SR algorithms. Well, let's actually have a look at the IGP metric on all the links on the topology. Here we can see, if I browse over router Frankfurt, I can see my IGP metrics across the different links in the topology. And in fact, if I were to go from Dublin to Frankfurt, you will see that my cumulative shortest path will be going through London with a cumulative IGP metric of 20. Well, I can also change my view of metrics to now the delay or the latency metric. These are actual measure MPLS, based on MPLS performance measurement, delays measure on the interconnected links between the routers in the topology. You can see as an example, the link between London and Frankfurt having a very high delay compared to the rest of the network, in this case 15,000 microseconds. This is in fact the view that we have in here. All the routers in the topology with the delay metric is in fact the view of the what we call the FlexAlgo 128. It is a slice that computes minimum delay across its members. I could also change the focus on the topology from the FlexAlgo 128 to the FlexAlgo 130. And you see what happened here is that the London side or the London POP has disappeared. The objective of FlexAlgo 130 is to minimize IGP metric to reach the destination while only using links that are encrypted. In this case, MACsec encrypted. London did not have any, so London disappeared. There were other links between routers like Barcelona and Milano that were unencrypted. While those links go away, only the encrypted facilities will stay in the view of this FlexAlgo. Let's now go back to the view of FlexAlgo 128 that includes London. I'm going to come back also, and we're going to take a look at the different policies that exist from Dublin to Frankfurt and vice versa for the different type of transport SLAs. We're going to click first in a policy that goes from Dublin to Frankfurt that attempts to minimize the delay. As you can see, the minimum delay is going to follow the path going over the green arrow. There is some delay between Dublin-London, London-Barcelona, but perhaps the biggest contributor is going from Barcelona to Frankfurt. This is going to be an approximately 1.5 to close to 2 millisecond delay from Dublin to Frankfurt, represented again by the path on the green arrow. If you take a look at the members of this seat list that is using this policy, you will actually find that only a single seed is used to represent this green line. So who is 17,031? You may remember the loopback. 17,031, which is the only seed of this policy, is the FlexAlgo 128 of node Frankfurt. Therefore, this policy effectively leverages the FlexAlgo for low latency as implemented by Frankfurt and the rest of the members. Well, let's now move on into another policy. Let's move into the policy that goes from Dublin to Frankfurt, going only over the secure slice. You can see now a completely different path that avoids London. It goes to Lisbon, then to Barcelona, and then on to Frankfurt. The delay on that path is going to be a little bit higher, but only uses secure encrypted links. We can roughly see that we're going to have around 2 milliseconds between Lisbon and Barcelona, 1 millisecond between Barcelona and Frankfurt. And yet again, if we look at the labels that are used in this policy, it's actually singular. One label, 18,031. Again, it is the FlexAlgo prefix seed of Frankfurt on algorithm 130. And if you remember, it's one loopback I have configured in Frankfurt with multiple personalities. The last policy to demonstrate here will be the policy that goes from Dublin to Frankfurt that simply minimizes the cost, the IGP metric. If you remember, this horizontal line was my combined or cumulative IGP cost of 20. But this is the path, on the other hand, that is going to experience a very high delay of over 15 milliseconds because of this high delay link between London and Frankfurt. This path is going to be represented again by only one label. In this case is the algorithm 0 label of Frankfurt, which it is the label 16,031. Now, if we click and we now go into the live graphs of traffic traversing our SD-WAN CEs, we'll talk more about them in a moment. We can see now, if you look at the right-hand side graph, is that I have 3 flows coming from the SD-WAN CPE behind Dublin going towards Frankfurt, and all of them have approximately a delay of 15 milliseconds. There is really not much differentiation that is going on in the service provider. All the traffic is going over a single IPsec tunnel and is just being delivered over the shortest path to the router, the egress PE that advertises the subnet for the prefix at the Frankfurt site for the SD-WAN customer. Well, we will leave that graph on, and what we're going to do now is we're going to go to Cisco's SD-WAN controller portal represented by vManage. You might have heard of the Viptela acquisition. So this is the Viptela dashboard in vManage. What we can see here is that there are 2 one-edge routers. We call them CH1, CH2. They're both using the CSR 1000B as we cover in the presentation. What we also have now is the ability to go into the policy area, and we have already pre-configured a policy called mobile policy. What's going to happen with this policy is that I am going to identify the flows that match these three lines I showed you in the previous graph, and I'm going to remark the outer DSCP that is going to be set to a specified value that the network operator will now be matching on and treating accordingly. Right now, the mobile policy that you're going to see is not activated. We're going to activate the policy, get a warning for it. Right now, the vManage is pushing the policy to the vSmart, and then from the vSmart, it's going to go down to the SD-WAN edge routers. Status is in progress. We wait for the policy to be applied on the CPE routers. Success. We come back to the previous graph on the portal, and now we see what has happened. We can see how my samples of latency for the three flows have dramatically changed. On one hand, I have my best effort traffic traversing the 15 millisecond path, which is the shortest path to Frankfurt. On the other hand, I have my red line that represents my secure sensitive traffic, my privacy sensitive traffic that goes to Frankfurt, avoiding London with a delay of around 3 milliseconds, and I have my absolute minimum delay for my delay sensitive application of around 1.8 milliseconds, which goes via London. Well, now, in conclusion, we can see how segment routing plays a significant role in SD-WAN. The service provider can monetize its rich infrastructure without adding any state into the network, and the enterprise can specify their own requirements, which flows require special treatment, when to activate such a treatment, and lastly, what type of path is needed. For more information related to segment routing, please stay up to date by leveraging the resources on the slide and follow us on social media. Thank you very much.